Okay. Okay. So in today's class, basically what we are interested is we are interested to know the transformer reactance calculations and how we go about the transformer. Prior to that, we will understand the yesterday's formula, how I applied for the number of cooling tubes. Maybe I have explained also, but I felt like it needs a little bit more explanation. So as you saw, when we are going for the design of the transformer tubes, what we do is that we take the area of the tank plus the tubes, then we minus the area of the tank with the tubes, and calculate area of one particular tube and get the number of tubes. This is one way of doing it. That is very simple. Now another way of doing it is like if you don't have these this much information available with you, so what you do is that you take the transformer loss into account, that is the eddy current plus hysteresis losses, and you equate it to the surface area of the transformer, and and with the heat dissipated area of the tube. So when we are going for the surface area, for example, temperature rise in a plain wall tank. If we are going for temperature, okay, here from here, it's a, yeah, temperature rise in a plain walled tank. For a plain wall tank, the temperature rise, we saw the temperature rise theta was equal to total loss in watts, that is total loss in watts divided by the total surface area, that was 12.5 st, wherein this 12.5 this dot is not coming, okay, 12.5 st. So you saw this is the formula for the temperature rise of the transformer. So as far as the total dissipation is concerned, as far as let see, basically what happens is that the st is the cooling surface area of the tank. Okay, so this this tank will dissipate 12.5 st watts per meter square per degree Celsius. That is heat dissipation by this tank would be. So we will write see here. So this heat dissipation by the tank, heat dissipation is due to two factors. One is your radiation, okay, and another factor is your heat dissipation, radiation plus convection. Okay, radiation plus convection. These are the two factors involved here. So we are interested to know how do we go about the calculation part of it. So basically, when we are going for this heat dissipation part, so what we do is that, so the total heat dissipation would be in the tank. So as far as the tank is concerned, in the tank the heat dissipation is due to the surface area, and in the surface area in the tank there is both convection and radiation. So the heat dissipated due to the convection, radiation is around 6 point, sorry, 6, whereas the heat dissipated due to radiation is 6.5. So the total heat dissipation in the tank would be 6 plus 6.5. Hence this you can see, hence this 12.5 has come. It is basically 6 plus 6.5. So 6.5. Okay. So hence this value has come. Now, when we are going for the design of a tank with tube, so dissipating surface area of the tank. See, as far as the tube is concerned, the tube is inside the tank. So basically, the surface area of the tank we have considered ST. This is what, this is surface area of tank. Surface area of tank. This ST is the surface area of the tank. Whereas dissipating surface area of the tube is within the tank, so tube surface area would be a fraction of the overall tank. So the dissipating surface area of the tank x time st. So sorry, this is the dissipating surface area. So we will write this is the dissipating surface area of tube. So this is the dissipating surface area of the tube. So the total loss dissipation in surface area of tank. So the total loss dissipation, if you see the total loss dissipation, total loss dissipation in tank, you have 12.5 times st. This is 12.5 times st. So st. So the loss would be st, and the it would be watts per degree Celsius. So watts per, what happened, per degree Celsius. So this watts per, so W got cancelled. Watts divided by. So now when you are taking the tubes into consideration, so by the positioning of the tubes, this dissipation due to convection gets improved by sometimes 35%, sometimes 40%. Usually we consider it by 35%. So what we will do is that the total, what is happening is, okay, it can also write without touching. I was not paying. Oh, wait 1 second. I'll clear this part. It is. So how many of you have joined? Hmm? I can see. Okay, here I cannot see. Bhamna, MCT, Chaitra. So 16 people have joined. Nice. Uh, so now what? Now the total loss dissipation we saw is due to the tube. Now we will go for the loss dissipation due to the tube. So the loss dissipation due to the tube. So same thing, total loss dissipation due to tube, you will see due to tube. So in the tube there is only thing, the loss dissipation in the tube is due to convection. So the convection loss is 6.5. Okay, but it is getting improved by 135%. So we can safely write it is 1.35 into 6.5, and the surface area of the tube, what we are in here, you see, we cannot directly multiply it with the st. We have to multiply it with the fraction of the area that tube is, x times st. Here why not x times, so the board is like till here only. I'll write it again here. This is equal to 1.35 x, okay, 1.35 into 6.5, 6.5 into x times st. So this is the total surface area, what you can see here. This part is not okay. So okay, so this is the total surface area. Now you saw that you have this and you have this part, and when you are like going for, when you are going for this part, yeah, when you are going for this part around, so it will come around 8 point, how much, it is coming around 8.8. So 8 point something. So we can write it safely, write it 8.8. Okay, so we can write it 8.8 times x times st. So this is the thing. So this plus this. So now when you have to go for the total loss, so the total loss dissipation, we can safely write the total loss dissipation. Total loss dissipation, how is equal to, 12.5 times st plus 8.8 times xst. Okay, so you can write like this. the total this loss dissipation is equal to like, okay. So now you tell me one thing. Now if you are encountering any loss as such, so what about the temperature rise and another factors that are involved in the calculation? How you are going to consider it? So the total loss dissipation is 12.5 times 8 times st. So there is one okay. So this is the formula basically we are getting it. But yesterday you saw that I applied a formula there directly. I wrote one thing. So now if you see that, if you see some certain commonalities between the area and the factors. So total surface area of walls of the tanks and tubes. So if you have, see, the total surface area of the walls, total surface area of tanks plus your tube is would be tank area, you know it is st, tube area, you know it is x plus st. So what you can do is that st is common, so it will become 1 plus x. So this is the total surface area that you are able to get with the this. Now you came to understand. So now the total loss dissipation, if I write my total loss dissipation, suppose my total loss dissipation, total loss dissipation, my total loss dissipation would be equal to how much? It would be equal to total loss dissipation would be equal to total loss dissipation by in surface area of tank and cooling tubes. So it would be equal to, I will write down, it would be equal to total loss dissipation, total loss dissipation in in surface in surface area of tank and tubes. So tank and tubes divided by total surface area of walls of tank and tube. So total surface area of walls of tank and tube. So this total surface area of walls of tank and tube we saw in the previous slide, we saw, see here. So the total surface, this is st1 plus x times, okay. So this is the value. And now the total loss dissipation in surface area of tank of cooling tubes. So the surface area also we saw. So the total surface area which we will get would be 8.8 xt plus this 12.5. So if you want to write the total surface area, so the total surface area you can get by C. The total surface area, if you want, this is the total surface, total loss dissipation, that is the total surface area of loss dissipation would be 12.5 st plus 8.8 x st. So this is the thing. Now if we have to calculate, go for this what we call is here, if we have to substitute, so total loss dissipation in surface area of tank and tubes. So what is the surface area of the tanking tubes? It's 12.5 st plus 8.8 x st. So x st. So we can write like that, 8.8 x st. So this is equal to the total loss dissipation. So we can also write one very good formula for this is, now we can generalize this in terms of, see, if you want to write total loss dissipation, total loss dissipation, we can write how much it is equal to, we can write it is equal to 12.5, okay, 12.5, what, tell me, 12.5, it is equal to 12.5 plus 12.5 st plus 8.8 x times st divided by st1 plus x. Okay, here we can take st common inside the bracket, we can write, okay, if we are taking st common inside the bracket, we can write 12.5 plus x 8.8. So this st 1 plus x, 1 plus x. So we can cancel this st and this st. So we will be left with 12.5 plus x 8.8. So this is 1 plus x. So one more, this thing we easily understood. Okay, this is like 1 plus x. And now let's understand how about the temperature rise. How can we relate this to the temperature rise? So the yeah, so the temperature rise, as far as the temperature rise is concerned, temperature rise within tubes. So temperature rise would depend upon what? Temperature, there would be theta, so the temperature will increase. See, so the temperature rise, if we have to go about the temperature rise, what we can write is temperature rise would depend upon total loss. Okay, it will depend upon the total loss, that is total loss, that is your pi plus pc, that is your iron loss plus your core loss, sorry, your loss in the copper and in the core, divided by your specific heat dissipation, divided by your specific heat dissipation plus your what? Plus your surface area. So this is like temperature rise. So in other terms, if you want to write this, you can write theta is equal to, so total loss pi plus pc, that is your pi plus pc divided by specific heat dissipation. So specific heat dissipation, so tell me, into surface area. So specific heat dissipation is due to what? Specific heat dissipation is due to convection and and radiation. So we, in the previous slide we saw that the specific heat dissipation, we got this 12.5, we got this 12.5 plus 8 x 8.8. So this was the, see, we move to the previous slide, here we got, see, total loss dissipation surface area of the tanks and the tubes. The third slide, if you see, yeah, here you got this value, this is the area. Here total loss dissipation was 12.5 st plus 8.8 x times st. So this is the same thing that you can incorporate here. Okay, so what we'll write, Ratika, tell me. Yeah, Afsa, Afsa, Noor, Ratika, Ratika, are
Yes,
you,
sir.
yeah, are you hearing?
Yes, sir.
Are you following
Yes, sir.
the classes? So okay, कोई नहीं बात भी okay, sorry. So the theta would be equal to pi plus pc divided by, so the theta would be equal to pi plus pc divided by the total loss. Now tell me, it would be equal to, Ratika, tell me, it would be equal to 12.5, sorry, like, I have to have an excellent hand-eye coordination for this. So it would be equal to, yeah, so it would be equal to 12.5 here. Theta would be equal to what? 12.5 plus 8.8 x times st. So you will write down here 12.5, okay, plus 8.8 x. st is common, I can take st out, so this is my one formula. Okay, so from this combination of this formula pi plus pc 12.5 st plus 8.8 x times st, I can happily write this here 12.5 plus 8.8x. Okay, 12.5 plus 8.8x times this, divide this into st, is equal to pi plus pc divided by theta. So pi plus pc divided by theta. Now if I need to calculate my x, okay, or if I need to calculate the value of x, see here pi plus pi plus pc divided by theta 12.5 st plus 8.8 x st. So if I want to still further I'll just rub this top portion because it would be much better to explain here itself. So let's erase. So here only because I will not having that much space. So okay, almost done. So what we can write is from this particular portion over here. See, from here I'm taking it. I'm writing it here. So what we will write is we can happily write generalize this equation as x uh, st 8.8 or 8.8 x 60 is equal to pi plus pc minus 12.5 st divided by theta, or else can be written as final expression can be written as x times st. X times st is equal to 1 divided by 8.8 pi plus pc divided by theta minus 12.5 st. So you can write this. So x times st is equal to, so what is the x times st? What does this x times st represent? This represents what? It represents total area of the cooling tubes. This represents, sorry, this represents total area of cooling tubes. So from this particular slide, you can see that now you can write the number of cooling tubes is equal to, so this represents the total area of cooling tube. So you can write the total area of, so the number of cooling tubes. So if you have to write number of cooling tubes, so the number of cooling tubes, how can you write? So total area of the cooling tubes, that would be total area of cooling tubes divided by area of one cooling tube. So area of one cooling tube, you know how to calculate. Area of one cooling tube is like pi d pi dt lt. So that is like your length of the tube. If you are like, if you want to go for the area of one tube, so it would be length, if length of tube is lt, dia of tube is dt. So area of a tube, area of one tube would be equal to pi dt lt. So now you can, number of cooling tubes n, you can write from the previous formula, total area of cooling tubes. So here you got the total area of the cooling tubes. Here you see. So this is x times st is what? Total surface area of total surface total area of cooling tubes. So total area of cooling tubes is, see, x times st is the total area. It is 1.88 pi pc theta minus 12.5 st. So you can write, okay. So you can write the formula. So this is 1 divided by 8.8, okay, 8.8 pi plus pc. This is the total loss, okay, divided by your temperature rise theta minus 12.5 st, close the bracket. Here you have pi dTLT, because this is the area of one cooling tube. So into pi dTLT. So the number of cooling tubes directly you can substitute in a formula. For example, like this. Okay. So if you are having very less time, so you can substitute. You have the values of the temperature loss would be given from there only. The total loss is for 4 kilowatt or 7 kilowatt. Write that 7 kilowatt. Temperature limit rise is 35. Write that 35. Surface area you can calculate 2 LTST plus 2 LTWT. LT length into height and length into width. Sorry, height into length and height into width, okay, for surface area, because you're neglecting the bottom surface, okay, only you're seeing the side cross sections. So now what you will do is that your n would be equal to, you calculate the value of st, so you can directly calculate the value of this thing. So that would be given, so your problem can be solved within 5 minutes. Another way of doing this for problem is that you first you total heat dissipated in the tank. If they are giving it total heat dissipated in the tube, then you can do total dissipation in the tank, or total surface area of tank minus total surface area of this thing, divided by area for each tube. So there are various ways of doing this problem. Are you clear? Did you get my point? And sometimes in one of the problems it was like somewhere I was doing one problem, it was like a means what? A, sometimes they will write A in a book. A means x times s theta. St, x times st. Okay. So those things you have to go back to the book also. Please pay attention. Did you get this? How many of you got? Radhika, you got?
Yes, sir.
Your doubt was there something. No, please ask something you asked that day. That doubt got cleared. How it is coming? Why I am taking like this? Yesterday, why did I do substitute like that? Hmm?
Yes, sir.
So you please just pay attention to this class. That's for you people only. I just wanted to make it little easier. So this is how it is coming. So we have today's class. I want to almost we have done majority of problems. So now I have to give assignment. All the problems I have taken, most of them, almost 90% of them are from VTO previous year solved papers. So what it does is that, so it gives you an idea like how VTO like functions. So maybe this time what I noticed is that they have not asked many problems on the reactance of leakage reactance. Only derivation they have asked, and they have this opportunity, they can ask for the reactance also. So let's do some problem I saw from the book. Let's try for the reactance problem also. Let's see how it goes. So this was about the this thing. So let's go do one problem, okay, and it will help us. Okay, so that is both you have to calculate the voltage regulation. Okay, so what is voltage regulation? Yeah, first you tell me what is voltage regulation. In the previous class also you studied about the transformer in previous semesters. What is voltage regulation? Voltage regulation is the figure of merit of a transformer. Figure of merit means what? Of transformer means if the voltage regulation is high, the transformer is good, or if the voltage regulation is low, the transformer is good. Radhika, you tell me. Hmm?
Sir?
If voltage regulation of a transformer is high, for example, it is 50, and another transformer voltage regulation is 25, which one is good? 51 or 25 one? Tell me. Anybody, Afsa, you tell me. Hmm? Noor, are you there? See, the other batches which team 24 and 4, they did not respond. So I have given 0 marks. We were asked to give 0 marks. So we could not help it. So because you are not responding, so the marks has given 0. So yeah, Nilakshi, Jyoti,
Sir, if voltage
Yes,
regulated
sir.
or
yeah,
it
yeah,
is
yeah. One person at a time. Yeah, tell me. Let one person speak. Then after that, another person. Yeah. Yes,
sir,
yes. Carry on. Yeah, yeah. Carry on. You only carry on. The last person only carry on. Carry on. Yeah, yeah.
Sir, voltage regulation should be low, sir, then efficiency will be high.
Voltage regulation should be low. So that means voltage regulation is basically if the voltage regulation is low, the efficiency would be high. So yeah, that is there. But what is basically voltage regulation is that it is the figure of merit, means how transformer is worthy for operation. Basically, voltage regulation is when you vary the transformer voltage from no load to full load. So when there is no load in the transformer, so basically if you are in your home and you are watching normally you are like in a normal scenario, suddenly what happens is that you put on a press for ironing your clothes or a iron, and for washing you need a geyser. Somebody switches on the geyser, so you will see there is a dip in the light in your house, little bit dip. So it was more bright prior to it, it becomes less bright little bit. If you notice it, sometimes you notice when you are putting a geyser or a press or a heating load, what happens to the light. So and what happens to the voltage, so voltage will go down a bit. So this voltage will go down a bit. So what down a bit in a transformer, what we do is that we load the transformer. So there is loading the transformer is means we can load the transformer by putting some load on it, and load on it till it reaches the full load. So when we talk about the load in case of a transformer, in the very beginning first classes I told you load also means current. So full load means the rated current of the transformer. So by that time, if we keep the transformer, so the rated current of the transformer is reached. In our house, we have fuse. What happens is that if we load the house beyond the transformer capacity, so what happens is that the fuse will blow out. If there is no fuse, the transformer goes. Sometimes we have to limit the transformer to see that we should not load it beyond its capacity. So the voltage regulation would be basically voltage. What is this? Uh, Voltage regulation, if we will write, so it would be basically voltage voltage at no load minus voltage at full load divided by, yeah, tell me, what's your name, Dikshita, divided by voltage at Dikshita, Dikshita TV.
Yes, sir.
So tell me what is voltage regulation. So it would be voltage at no load minus voltage at full load. So if we have to define it, the definition of voltage regulation would be variation of voltage from no load to full load by keeping the sending end and voltage constant. This is very important. This thing is very important. By keeping the sending end, this thing here you saw, you have to keep the sending end voltage constant. So whenever you are putting some load on the transformer, so what happens is that you have the sending end voltage 220, okay, So both there would be a dip in the sending end voltage, so it will also get dropped by putting the full load. Full load you will see by the current rating. Okay. So what now you have to do is that by keeping the sending end voltage constant, so you will have a variac auto transformer. With the auto transformer, whatever is the rated voltage of the transformer, you have to achieve that rated voltage back after you are putting the full load. Then only you will get voltage regulation. If you are not getting the rated voltage back, simply you have put the load and you are subtracting load at the sending end, that is the no load, and load at the receiving end, you will get a wrong formula or the wrong percentage for voltage regulation. So this is about the voltage regulation part. And now in this particular voltage regulation, you have seen in the previous classes also, if you have the percentage voltage regulation formula also, that you is like we have limited scope, so that formula we have seen in the previous semesters also. You can see the books for this percentage regulation. We can write in terms of your current also, in terms of your losses and efficiency. You have that, because of that only this girl told me regulation should be low, the efficiency will improve. So that formula is there now, that is relating regulation to efficiency. We can write ip rp cos phi plus ip xp sin phi divided by your voltage at your primary, divided by V1 or the primary voltage. So this is basically the voltage regulation. In percentage, you have to multiply here, not in the denominator, that is in the numerator only. I will write down here again. That is IP RP cos phi plus IP XP sin phi x times into 100. So this is your voltage. You have seen that formula, Dikshita? Huh? Radhika?
Yes, sir.
This formula you have studied in your previous semesters, isn't it? Huh?
Yes, sir.
Yeah, if you are not remembering, just reopen previous semester, because everything it is not possible. Like each and everything I cannot explain, but I'll put, like, if we get time, I'll put some video. So let's go for one problem because we have some time. 15 minutes is there. I'll do half of it. Half of it you'll do. Calculate the percentage voltage regulation. I'm writing as VR at full load, at full load, zero point 0.8 power factor, 0.8 power factor at full load, 0.8 power factor lag. Okay, lag. So till here only it writes my board. Huh? Okay, 0.8 power factor lag for a 500 kVA 6000 400 star, no, 400 delta star, it's delta star, three phase 50 hertz transformer, transformer having having following having following data. So what is the data the transformer is having? So the height of the coils. So the height of coils is equal to 48 centimeters. So data we will write in some other color, it will look good. Okay, height of coil is equal to 48 centimeter. Thickness of LV and HV coils. So this is thickness of HV and LV coils. Thickness of HV and LV coils is equal to 2.53 centimeter, 2.53 centimeter and 1.65 centimeter. So this is the second data it is given. Insulation between LV and HV coil. So this is insulation between HV and LV coils. This is the insulation between HV and LV coils. The insulation is 1.4 centimeter and your mean diameter of coil, that is your mean dia of coil, is equal to 28 centimeter. Your volt per turn, your volt per turn is equal to 8 volt, and your full load copper loss, that is your full load copper loss is equal to 3.8 kilowatt. So this is your problem. So we can see that the transformer, as here I'll just take the highlighter. So as a transformer here, in the primary we have 6000 volts, and in the secondary we have 4000 volts. Can we calculate the number of turns? So we have the formula also. We can write that for the number of turns. We have this A is equal to NP by NS is equal to Vp by Vs. So instead of NP we can write TP by Ts also. So the number of turns VPVS is there. So VP is 6000, this is 400, and we need to calculate. So we have also one more thing is there. If you see that, so turns, volt per turn ratio is there. Volt per turn is 8 volt. So you can calculate T1. If you want to calculate T1, you can directly write primary 6000 divided by volt per turn is 8. So number of turns is 6000 by 8. Similarly, once you get the value of T1, you get the value of IP. So IP value is would be what? KVA rating is what? KVA is VP into IP. So primary current, it's a three-phase transformer, so it would be 3 VP into IP. So that is your KVA. So KVA is mentioned here is 500 KVA. So 500 would be 3 VP into IP. VP is given 6,666,000. You can get the value of IP from this particular problem. So VP is given, so you get the value of IP. So what else you can do apart from this? Tell me. So similarly, how do you proceed? So first, whenever we have to go to do a problem, first we have to think what they are asking, what is the data given. So carefully read 2-3 times, and then we have to go about the problem. It is not like that. Okay, the problem is there. We are seeing it. We have not seen before. So maybe we have not done it. So maybe we will not be able to do it. This is not the procedure to approach a problem. So whatever information you have to apply, like apply to do any problem. If you have to do, you have to apply that information that is available with you. So the information till now what available with you is that how we will go about the calculation part of it and how do we go about it. So I want you, what would be the next step? Any one of you can tell me how you will follow it, what procedure you will apply to calculate these things. So I'll wait for 1 minute. Please tell me, give your reactions. I want to hear some reactions. Tell me. That means you are not following anything. Okay. So one thing is that it requires a bit of logic. Like if you are applying for gate examination also, the things would be pretty obvious over there. But only thing is that you should be able to see the catch and the link between the problems. So it won't be a different problem. So I gave you a clue. Number of primary turns you calculate, primary current you calculate. So once you are calculating the primary current, okay. So for the leakage, it's asking for the voltage regulation. So for the voltage regulation, we know that it would be IP RP cos phi plus IP XP sin phi V1. So that means we have to calculate the value of resistance, primary resistance. We have to calculate the value of reactance. See, cos phi is available with us. Why? Because the power factor is zero point 0.8. Sin phi will come automatically zero point 0.6. V1 is given 6,000. Only thing we need to calculate is IP, RP, and XP. So IP, I showed you how we calculated. Now about the RP. So the full load copper loss. So the copper loss means the loss in the copper, and the loss in the copper is due to the resistance in the copper. So for a three-phase copper loss, it would be 3I square RP. So the full load copper loss is also mentioned. So 3I square RP is equal to 3 IP square RP is equal to 3.8 kilowatts. IP also we calculated previously. Now from this you get the value of RP. So once you get the value of RP, now the only thing that is left is that you have to calculate the value of XP. So XP is what? XP you can calculate from the leakage resistance reactance formula, that is your 2 pi f Tp square mu naught LMT LC A that we have seen in previously, A plus, tell me, B1 plus B2 divided by 3. So this XP, once you got, you have to resubstitute. This thing you should do on your own, because I, yeah, Ratika, did
Yes,
you
sir.
understand what I mean? What I meant, what you have to calculate? Percentage voltage regulation, okay? So you have to get this value, VR value you have to get. So VR value would be IP RP cos of phi plus IP XP sin of phi divided by Vp. Okay, this is the percentage. So IP value you can calculate 3 Vp. IP would be equal to your kVA value. Okay, the kVA value is given. Okay, then RP value 3 IP square RP would be equal to your full load copper loss, full load copper loss. Then your XP value is that leakage reactance formula that we saw. How we calculate the leakage reactance formula, we saw no previously. What was that leakage reactance formula? It is, you can write the formula 2 pi f. Okay, what was that? 2 pi f mu naught 2 pi. So this is like XP would be given by 2 pi f mu naught TP square LMT LC A plus B1 plus B2 divided by 3. This we also calculated in the derivation. Ratika, uh,
Yes, sir.
this we calculated in the derivation, this XP reactance formula. So you have to substitute these formulas, like you get the value of XP, get the value of RP, get the value of your IP, and see, substitute here. VP value is given 6,000. This is given 6,000. Power factor cos phi is given. Cos phi is zero point 0.8. So sin phi would automatically come as 0 0.6. So 0 0.8, 0 0.6. VP given. Only need is that IP, RP, and XP you need to calculate. So now I want you people to solve this problem. At least give me the value of IP. I'll be waiting, because every time if I do, the problem is like, those of you who are joined late, please read this. Calculate the percentage voltage regulation at full load, zero point 0.8 power factor lag for a 500 kVA, 6,000 divided by 4,000 delta Y three phase transformer. Now it is also very, one thing to note is that delta star connected transformer is there. So in the primary side there is a delta, in the secondary side there is star. Here it is not affecting, this arrangement is not affecting to our final calculation, but sometimes this arrangement can affect. Like in the primary, if it is delta is connected, then your V primary uh, see, you need not divide your 6000 by root 3 because your V phase is equal to V line in the primary side. So if it was star connected there, so you had to divide this 6000 by root 3 because your B phase would not be equal to your V line. Now that it is in delta connected, so here your V primary would be equal to 6000. Now if it was star connected here, it was vice versa, star delta. So your primary should be divided by root 3. Are you understanding my point, Ratika? Ratika?
Yes, sir.
Yeah, are you doing it? Please do. Please calculate the values. At least calculate the value of IP, RP. XP later we will see. And then this is your homework also. At least do some portion from this. You can do. I'll keep the problem. You know, note this down. Whenever you are sitting in the classroom, sit like a pen, copy, calculator, everything. Take it very seriously. Like this, if you just see like a movie, it will not help. If you are sitting and for studying, then sit for study. Now you that complained it was blur something and all that, I understood. I also felt after seeing my videos. Now I'm trying with this. At least now we have so much facility available. We can go back to the problem, we can read the problem, we can resubstitute. See here, VP value is given 6000. Three phase it is given. So you have the transformer voltage is also given, kVA, that is 500 kVA. So 500 kVA would be equal to 3 VP IP. So 3 VP value is 6000 into IP. So it would be, IP would be equal to 500 into 10 power 3 divided by 6 divided by 18,000. So 18,000 divided by, so divided by, so it would be around 500, it would be around 5 lakh divided by 18,000. So 5 lakh divided by 18,000, how much it will come? Hmm? At least calculate the value of IP. Tell me. But to calculate the value of IP, so it would be how much? 27.7.
Milliamps, sir.
You're getting in milliamps.
No, sir. Ampere only.
Ampere, it would be ampere. 27.7 amps. Because 500 into 10 power 3 you have to do. You are, I think you are not done into 10 power 3. That's why you
Yes,
are
sir.
taking,
I
yeah,
got, sir.
yeah, that's why you are telling milliamps. Okay, then your primary resistance to calculate, that again would be 3 IP square RP. So 3 IP square RP is equal to, they have given 3.8 kilowatts. So you will get the value of RP, 3 IP square, 3 IP. Now your IP value we calculated 27.7. So 3 into 27.7 into R, 3 into 27.7 ka whole square into RP would give you is equal to 3.8 kilowatts. Like primary students, you are not doing. Why you are not doing? Do this. Yeah. So now the time of this session is like almost getting over. So please, when you are coming to the next session, I need 4 volunteers. We have to do 8 flip classes. So I will not give you much time in the next flip class. I need 7. I need a flip class. I need around 3 people to give flip class, and 7 minutes for each because I have to carry on with the induction motor. So I'll give 20 minutes for flip class and rest 40 minutes I'll do my lecture. So tell me, Afsa, are you there? Afsa, Nilakshini, Nilakshini.
Yes, sir.
So you have to give your flip. Everybody has to give the flip class. So you have to give your flip class. So you can choose your topic. You can give on cooling, or you want to give on reactants, or you can give on arrangement of tubes, whatever you want.
Okay, sir.
You can give. You will give on cooling of tubes.
Okay, sir.
Okay, good. So Nilakshini, Afsa will give on arrangement of that reactance calculation. So tell to Afsa Firdos, give on reactance calculation.
Yes, sir.
And Noor is there. Noor. So also you inform to Noor that she will give on in the transformer only. She can give on what we say is that she can give on voltage regulation. Okay, what is voltage regulation of a transformer, and this calculation of the voltage regulation in terms of reactance. Okay, Nilakshini, Nilakshi, yeah,
Yes, sir.
you communicate it to Noor. So on Monday we will have first 20 minutes would be your flip class, and then we will start with induction motor. And please do this question, it's very important. Till now this type of question has not appeared in the an examination. Now the corona is there, we never know, it can go also, the way it came it can go. Like in 1918 Spanish flu came, it remained for 2 years, it went without any invention. Similarly it can happen, and finally you are sitting in the examination, V2 examination, you are not well prepared, so we should be 100% prepared. So this type of question can also come. So
Sir,
those
can you repeat the topics, sir?
so for you, cooling of tubes, okay.
Okay.
For AFSA it would be the reactance calculation, okay.
Yes, sir.
For Noor it would be the voltage regulation,
Okay,
okay.
sir.
You please take it down, okay. And Monday you have to give, I will post, okay. Okay, then you can we'll wind up the class, I'll stop recording, and you please put your attendance, you'll please put your attendance.